Let's talk about a world right here in our own solar system where the rules of time just get thrown right out the window. We're heading to Mercury, and we're going to figure out how a single day can somehow last longer than an entire year.
You heard that right. One single sunrise to sunrise cycle on Mercury takes twice as long as its whole trip around the sun. I mean, that just sounds wrong, doesn't it? It feels like it completely breaks the rules for how a planet is supposed to work.
So yeah, how is that even possible? It seems to defy all logic, but the answer isn't some kind of cosmic magic. It's all about physics. And to solve this little mystery, we need to start with the numbers.
Okay, so to get our heads around this whole paradox, we've got to get the basic numbers straight first. Let's just take a look at how time on Mercury stacks up against time here on Earth. First up, Mercury's year. That's the time it takes to do one full lap around the sun. And that journey is super quick, just 88 of our Earth days. Now for its spin. Mercury takes about 59 Earth days to rotate once on its axis. So, so far nothing seems too out there. The spin is slower than the orbit, sure, but the math still doesn't get us to a day being longer than a year. So what are we missing here?
And here it is. This is the final piece of the puzzle. The time it takes for the sun to get back to the exact same spot in Mercury's sky, what you and I would call a day, is a staggering 176 Earth days. That is exactly twice as long as its 88-day year.
So how on earth do we make these numbers make sense? Well, the clue is realizing that there's more than one way to define a day. You see, the cosmos has a couple of different definitions, and on a place like Mercury, that difference, it means everything. All right, so on the left, we have what's called a sidereal day. That's the 59 days, how long it takes Mercury to spin once compared to the distant stars. But on the right, that's the solar day. That's the one we actually care about for sunrises and sunsets. It measures the time for the sun to return to the same spot in the sky, and crucially, it has to factor in that the planet is also zipping along in its orbit.
Now here on Earth, this difference is tiny. Our solar day is just about 4 minutes longer than our sidereal day. No big deal. But on Mercury, because it's orbiting the sun so fast while spinning on its axis so slowly, that little 4-minute difference, well, it blows up into something absolutely massive.
Okay, so now we get to the real reason why all this happens. This isn't just some weird coincidence. It's because Mercury is locked in this stable gravitational dance with the sun. It's a phenomenon called spin-orbit resonance. It sounds a little complicated, but all it means is that the sun's massive gravity has kind of nudged Mercury's spin and orbit into this fixed, repeating rhythm, like a kind of gravitational harmony. And for Mercury, that gravitational harmony is locked into a very specific, very clean ratio, 3:2. This simple little fraction right here, this is the secret code that explains everything about the planet's bizarre sense of time.
So what does a 3:2 resonance actually look like? It's pretty simple when you break it down. For every 2 trips Mercury makes around the sun, that's 2 of its years, it spins on its axis exactly 3 times. This perfect, repeating cosmic dance is what stretches its solar day out for so long.
Now, this isn't just some fun piece of space trivia. This ridiculously long day has some pretty dramatic and frankly brutal consequences for the planet itself. It creates a world of shocking extremes. Think about it. With a day that lasts for months, the side facing the sun has a long time to just bake, reaching a scorching 430 degrees Celsius. At the same time, the night side is plunged into a prolonged, deep freeze, dropping to a frigid -180 Celsius. And with practically no atmosphere to spread any of that heat around, you get one of the most violent temperature swings in the entire solar system. These insane extremes also create some really unique geology. And what's maybe most amazing is that they actually allow ice to exist. Yep, in deep craters near the poles that are always hidden from the sun's direct rays, you can find water ice, just sitting there on the planet closest to our star.
I mean, just try to picture that for a second. You'd watch the sun slowly crawl across the sky for 3 straight months, and then you'd have to survive an equally long and brutally cold night. Our whole concept of day and night would be completely meaningless there.
So, besides just being a fascinating oddball, why should we care about Mercury's weird timing? Well, because understanding these kinds of extremes teaches us some really fundamental lessons about how planets actually work. Studying this 3:2 resonance helps us test our big ideas about how planets form and settle into their orbits. It's like a perfect real-world lab for testing the laws of gravity, and it just shows the incredible, wild diversity of worlds that can exist, even right here in our own neighborhood.
And that really is the heart of it, isn't it? Mercury is this powerful reminder that our experience of time here on Earth is not universal. The cosmos is just filled with places that play by their own set of rules, forcing us to constantly rethink what's even possible.
Which kind of leaves us with one final thought. If something as basic as a day can be twice as long as a year, what other fundamental rules are just waiting out there in the dark for us to discover?